Howdy, folks. Welcome back. So this is our last day of class before break. Remember, on Monday we have the test, so don't forget that. But the test I'm just going to post on Katie like last time and give you time to finish and turn in just like last time. So today, in advance of the test, I am intending to just take your questions and answer them. So there's a lot of questions that have already poured in to the question bank, so I'll go over those, but also any additional questions that come up as we go over these various things. I want to make sure I address those as well. So, first of all, maybe the easiest to answer question is some people asked, what on earth was happening with question 46 on the homework? And the answer is that when I was editing the homework, I accidentally separated question 46 from the parts of the question below it. So question 46 was just a definition that didn't ask anything. And so I have reset it. Basically, if you read it and you read down a little further, below 48 was this giant list of questions that concerned the definition. But just to make crystal clear, I uploaded a version of the homework where everything is grouped correctly. Sorry about that. So that question should be resolved from that. Someone asked in the video where I did some classic proofs and also did some weirder examples of proofs. The two that were classic proofs are the fact that square root of 2 is irrational, and there are infinitely many primes. Those were the classic ones. And then the others were examples of stranger proof methods. Someone asked about the difference between proof by contrapositive versus proof by contradiction. And so these are completely different things. So let's review proof by contrapositive. This is a method of proving an implication. And it's the method where we instead prove not Q implies not P. Okay. So proof by contrapositive is really just a tiny tweak on direct proof. Because ultimately in proof by contrapositive, you end up giving a direct proof just of a slightly different statement, namely of the contrapositive of the original implication. And this all hinges, again, on the fact that the contrapositive and the original implication are logically equivalent. So whichever one you want to prove, you always get that choice. Proof by contradiction. Okay, and then on the other hand, proof by contradiction is a method of proving theoretically any statement. And basically, the way it works is that you consider the counterfactual. That is, you consider not P. And then what do? You identify a fundamental flaw with this universe. Okay, so that is sort of the difference here in terms of styles. So we've done tons of proofs by contrapositive. Proofs by contrapositive are, I mean, to the extent that anything in this class is algorithmic, at least the structure of a proof by contrapositive is algorithmic. You suppose not Q, you do some work, maybe a proof by cases, maybe all these other sorts of things, and then you get to not P. Whereas a proof by contradiction is more subtle, because in a proof by contradiction, you're sort of placing yourself in this universe where the thing you're considering is false. And you know, if the thing you're considering is false, that this universe in some sense must not make sense. It's in some sense broken in some fundamental way, and basically you do a proof by contradiction by finding what that fundamental way in which this universe where this thing is true is broken is, and articulating it. And so when you start a proof by contradiction, you don't really know where you're going. You know where you've started, and so you can sort of just deduce things and prove things in every which direction, but you only actually finish the proof by contradiction when you're able to clearly articulate what it is that's wrong with the world where this thing is true. So, for example, in the video, I did the proof that the square root of 2 is irrational, and we did this by contemplating the universe where the square root of 2 actually is instead rational. And the thing that turns out to be weird in the universe where square root of 2 is rational is that the square root of 2 turns out to be a rational number that it's impossible to write in lowest terms, which doesn't make any sense because we know a specific algorithm that we learned in elementary school for writing a fraction in lowest terms. So that's a big distinction between these two things. Okay, so that is proof by contrapositive and proof by contradiction. As I said, it's going to be pretty rare for you to have to produce a proof by contradiction. I'm not sure I've ever really found a great example of a homework or test question to ask in this class that really requires proof by contradiction in a natural way. There's certainly plenty of questions on the homework that you can use proof by contradiction to answer if you prefer, but it's really hard to come up with questions where it's obligatory. Someone asks, when you're using a proof, or when you're doing a proof by induction and you're writing some equation where you're simplifying it or whatever, I always put, when I'm doing it, this phrase, something like by the inductive hypothesis or by assumption or whatever. And they ask, do you have to do that? And the answer is yes. If you're going to use the thing that you assumed, you need to say that the reason why you're allowed to do that is because you assumed it. Now, one way to do that is to actually use equation array in LaTeX. So if you were writing this for a senior paper or something fancy, you would use this. Or is it began equation array? But either way, this is sort of like the fancy way to do it. But for your homework for this course, it is certainly sufficient to say something like write down the algebra and then write where the third equality follows from the inductive hypothesis or whatever. So this is definitely sufficient. You don't have to go into the figuring out how to get an equation to line up where you actually can write the text in line next to the equation, though you can if you want. So I've outlined proof by contradiction as a method of proof. Someone asks if it can also be used as a method of disproof. And the answer is yes. That is absolutely true. However, I want to mention that proof and disproof are nearly synonyms. And now, of course, in some sense, proving something and disproving it are as far apart as it is possible to be, because one is saying the thing is true and one is saying the thing is false. But a proof of P is a disproof of not P, and a proof and a disproof of P, I guess I should say, is just a proof of not P. And so disproving something is the same as proving its negation. And so disproof is not a fundamentally different kind of thing than proof. They're really, both are proofs. It's just a question of, is the thing that's written the true thing, or is the negation of the thing that's written the true thing? And so I think a lot of the distinction here comes from the fact that we tend to associate disproof with counterexamples. But if you go back and look at when we first talked about counterexamples, only very specific kinds of statements get disproven with counterexamples. Namely, what kind of statement is it that you can disprove with a counterexample? What does it have to start with? Oops. For all, right. For all statements get disproven with counterexamples. Oops. Counterexamples. Okay. On the other hand, a there exists statement is typically proven with an example. And so, again, it's all a matter of what the statement is, what a disproof is going to look like. But again, here, the real thing that's going on is that, again, proving P is the same as disproving not P, and the negation of a for all statement is a there exists statement, and the negation of a there exists statement is a for all statement. So that's how all of this sort of gets bundled together. But anyway, to go back to the specific question, can you use proof by contradiction to disprove a statement? The answer is absolutely. Proof by contradiction in principle will let you prove anything, including the negation of a statement or any other statement that you want to look at. Okay, and then before I jump into talking about all the questions on the homework that people have, I wanted to answer this one last question, which is about what does it look like to alter the inductive step, and how do you know you have to? So this is really going to come from a matter of understanding what sort of, again, the basic version of induction looks like. So I keep drawing this, and I think this is really helpful, at least to me, in terms of visualizing this, that what basic induction does is to prove a base case and also prove that you can always go from the thing being true for k to the thing being true for k plus 1. So a statement about k implies same statement about k plus 1. That's the inductive step plus base case. That's sort of the usual formula for induction. Okay. So when do you need to modify your inductive step? You need to modify your inductive step when the statement about k doesn't by itself imply the statement about k plus 1. So in other words, knowing that whatever this thing is true for 7 isn't enough to conclude that it's also true for 8. And so the modified inductive steps, we've done a lot of different kinds of modified inductive steps, all come down to, okay, well, if knowing the statement is true for k alone doesn't tell me it's true for k plus 1, what is enough to tell me it's true for k plus 1? Okay, so alternate inductive steps. Okay, so we've seen, for example, it be the case that the statement being true for k implies the statement is true for k plus 5. Or for k plus 2, or k plus any other number. So instead of going from one lily pad to the next lily pad to the next lily pad in our analogy, our frog has to sort of jump all the way to 5 lily pads ahead. But maybe this is the natural thing to prove. And if this is the natural thing to prove, that's fine. We just need more base cases. And so in this particular case, it would require 5 base cases in order to use this inductive step instead. Now, another form that we've seen, and this has showed up a lot, for example, when talking about things with Fibonacci numbers, is where the statement is true not just for k, but also k minus 1 implies the statement is true for k plus 1. So it's not enough to know that it's true for the previous case. I need to actually know it's true for the previous 2 cases. Okay. And so this often shows up, as I said, with Fibonacci numbers or whatever. And so here we'd need 2 base cases. But once I have the two base cases, then this form of the inductive statement would be sufficient to prove the result. And then next, and this is sort of the final form of this that I think we've talked about, is the statement is true for 1, 2, 3, all the way up to k, implies the statement is true for k plus 1. So sometimes you might need not just the previous case or not just the case from 5 ago. Maybe you need all of the previous cases. If you need all of the previous cases, then you can use an inductive statement like this. Okay. And so how do you know you need to modify the inductive step? You need to modify the inductive step, again, when you can't prove the quote-unquote standard inductive step. That is, when you can't prove that the statement about k implies the statement about k plus 1, but you can prove some variation of one of these other things. Okay, questions about alternate inductive steps? Okay, so let me give you an example of a question where pretty naturally you need a different inductive step. Okay, so here's the question. The question is to show that if I start with a square, and I've just said geometric square to make sure you know I'm talking about the actual shape a square and not a number like 9 or something like that. I want to show that I can break this into smaller squares as long as I choose the smaller squares correctly. So here is one example of doing that. Okay, so this is 1, 2, 3, 4, 5, 6, 7 squares. And so this is what I'm talking about, is I am talking about breaking the square into smaller squares in some capacity like this. So here I have broken a square into 7 smaller squares. Here, I've broken a square into, I think, 6 smaller squares. Okay. Now, these two examples actually show you that maybe it's going to be pretty hard to show that if it's possible to break a square into k squares, then it's possible to break it into k plus 1 squares. Because, for example, I think it's going to be awfully hard to come up with some way that I can change this picture into this picture. But if you play with it a bit, you'll figure out that what you actually can prove is that, so this is my inductive step. And so here's the thing you can prove. If it's possible to break a square into k smaller squares, then it's possible to break a square into k plus 3 smaller squares. And here's the proof of that. Let's suppose it's possible to break a square into k squares. So that means I have some picture here where there are k squares. Well, I'm going to take this exact square and reproduce it here. And then I am just going to add a copy of that square, but empty, here. And there, and there. So this is 1, 2, 3 squares, plus the k squares that are here from before. And so as soon as I can break a square into k squares, I can always break it into k plus 3 squares. Okay. And just to put a couple words with this, what this picture is showing you is that if it is possible to break a square into k squares, it's possible to do it in k square or into k plus 3 squares. You will not be required to put any pictures in LaTeX for this test. It's a valuable skill, it's worth learning, but I am not going to make you learn it on the test. Okay. So this is a modified inductive step. And so my question is, okay, if I modified this inductive step like this, what do I have to do for base cases in order to make this inductive step prove the statement I wanted to prove? Right, I also need an n equals 8 base case. Okay. So 6 I already showed you. 7 I already showed you. Okay, here's 8, 9, 10, 11, 12, and so on. Okay. And now by this inductive step, the fact that I showed you how to do 6 also shows you how to do 9, which also shows you how to do 12, and so on. That covers every multiple of 3. The fact that I showed you how to do 7 tells you how to do 10 and 13 and so on. So that covers all the numbers that are 1 more than a multiple of 3. And so to finish this proof, all we need to do is this one more base case. Which would be n equals 8. And so this is how you sort of fall into learning that you need to modify your inductive step. You figure out, okay, I can't quite see how to get from n to n plus 1, but maybe I can figure out how to get from n to n plus 3, which is what happened in this example, or maybe I can figure out how to get from k minus 1 and k to k plus 1, or variations thereof. And so once you've figured out what you actually can prove for your inductive step, you can then go back and figure out, okay, what do I need for my base cases, and figure out those. I will leave it for you to figure out how to break this square into 8 squares to finish this proof. I think this is actually a rare example where the base cases are actually harder than the inductive step, at least once you know what the inductive step is supposed to be. All right, so I intend now to talk about homework questions, but before I talk about homework questions, are there any additional questions just sort of generally about any of the things we've done so far with proof methods, logic, negation, all of these sorts of things? Okay, so here are the questions that people have asked me to talk about, at least a little bit. So let's talk about these questions. Okay, so 46, I think part of the issue was the fact that it was numbering. So the old 46 is now the new 48 with the numbering just because I put the groupings together. But let's start at 41. Oh, was it 41A or B? B, 41B, okay. Okay, so here we want to find a formula for 1/2 plus 2 over 2 squared is 3 over 2 cubed plus 4 over 2 to the 4th up to plus n over 2 to the n. And so we want to make a table, so I'm going to call this thing S sub n uncreatively. Okay, and why am I making a table? It's because this question doesn't actually tell me what I'm trying to prove, so I have to make enough data to figure out what I'm trying to prove. Okay, when I add this together, I am going to get 1. Okay, 1 plus 3/8, this will be 11/8. 11/8 plus 4/16 would be 13/8. 13/8 plus 5/32. We have exceeded my capacity to do this in my head. Let's see, 13 times 4 would be 52. Yeah, 52 plus 5 would be 57 over 32. Okay. So I suspect the question here, although you can tell me if I'm wrong, is really what on earth is the pattern here? And so here's my hint to help you uncover the pattern. Figure out what the denominator is supposed to be. Okay. And so the denominator here is 2. Here the denominator is 1. But actually, if I look at this and this and this, I can kind of guess what the denominator is supposed to be here. Namely, the denominator here is supposed to be 4. So I'm going to rewrite that as 4 over 4. And likewise, the denominator here is supposed to be 16. So I'm going to write that as 26 over 16. And so now, I think there's a little bit clearer of an idea as to how to write down a formula for these things separately, so the numerator and the denominator. So instead of looking at this list of rational numbers, now look at the list 1, 4, 11, 26, 57 of the numerators, and then the denominators are 2, 4, 8, 16, 32, and you know how to write down a formula for that. So this is my hint for how to proceed on this one. Okay. Next up, people asked about 43. Okay, so this is prove that if x is an R, and x plus 1 over x is an integer, then so is x to the n plus 1 over x to the n for all x in z plus. Sorry, all n in z plus. Okay, and so the hint here is to look at x plus 1 over x times x to the k plus 1 over x to the k. Okay, so if I multiply this out, x to the k plus 1 plus, let's see, 1 over x to the k minus 1 plus x to the k minus 1 plus 1 over x to the k plus 1. And so the key thing here that I can make much nicer is that I can define my own notation. So let's go ahead and let a sub n, I'm just going to use that to denote this x to the n plus 1 over x to the n. And so what I want to notice here is that this is, well, that's a sub k minus 1. That's a sub k plus 1. Okay. And the two things I multiplied together were a sub 1 and a sub k. Okay. So in terms of the problem, which is really show a sub n is an integer for all n in z, sorry, all n in z plus, I know this relationship among the various a sub whatevers. Now, it turns out this isn't the most helpful way to write this. Probably the most helpful way to write this is as a sub k plus 1 is equal to a sub 1 times a sub k minus a sub k minus 1. And so here's the key. This piece that I've boxed in red actually shows us that the following inductive step is true. Which is that if I know that all of a sub 1, a sub k, and a sub k minus 1 are integers, well, then of course, if all three of these are integers, then the product of two integers minus a third integer, that's an integer. And so that tells me in particular that ak plus 1 is also an integer. Okay, and so basically by just following this hint, I sort of fumbled backwards into what my inductive step is supposed to be. And so this is a kind of weird looking inductive step. But once this is my inductive step, then I know what I need to make my base case. Namely, what do I need as my base cases in order for this inductive step to work? Okay, so just to reiterate, my question is, if I want this inductive step to carry me through everything, what do I need? And that's right, I need the n equals 1 and the n equals 2 base cases. And again, I can figure that out by thinking about my list of things I want to prove this for. So here's 1, 2, 3, 4, 5, and so on. Okay, so in order to get somewhere, I need to know the previous 2 places as well as 1. So if I want to get to 2, I can't do that with this inductive step, because in order to get to 2, I would need to know this thing for 1 and for 0. But that's not part of what I'm talking about. So I, in fact, can't get to 2 other than by proving it directly. So I'll need as my base cases n is 1 and 2. But once I have those base cases, now when I go to look to 3, I do have the previous 2 statements, so I'll get 3. These 2 with their power combined give me 3. And now, in fact, these 3 with their power combined give me 4. These 3 with their power combined give me 5, and so on. And so that's how I end up getting everything. Okay. Now, how do you actually do these base cases, just to make sure we write that down? Okay. The n equals 1 base case is literally the assumption of the problem. So going back to the statement of the problem, if x is a real number and it so happens that x plus 1 over x is an integer, then so is this thing. This is the n equals 1 base case. Okay, so we get to assume the n equals 1 base case. So then we have to prove the n equals 2 base case. And so here's where we want to use this formula from before. So by our formula, a sub 2 is equal to, and so here I'm taking k equals 1. I'll get a sub 2 is a1 times a1 minus a0. But what is a0? Well, in this instance, a0 is just 2, right? Because it is x to the 0th plus 1 over x to the 0th. And x to the 0th is always 1. So this is a1 squared minus 2. Okay. And so since a1 is an integer, this is definitely also an integer. And so that finishes my base cases here. Okay, any questions about that? Okay, so now we have entered the realm of where I changed the question order a little, so I will write just what the question's about. So the P3 set question, which should be 48. And I think people just wanted me to talk about the definition of P3 set and core just to make sure they understand what these two definitions are saying. So, namely, the definition of a P3 set is a subset S of Z plus is called a P3 set if there exist X, Y, Z in S, not necessarily distinct, such that X plus Y plus Z is prime. Okay, so it is a set of positive integers with the property that there are 3 elements in the set whose sum is prime. Okay, and those 3 integers need not be distinct. And I do want to emphasize, by the way, this not necessarily distinct phrase is just a nicety because I've seen people do this question before and forget about this. But even if I did not say this, it would still be implicit in the notation that any variables I pick could be the same unless I specify that they cannot be the same. Okay, so what are some examples, just to make sure we're clear on this? So let's see, is this a P3 set? I claim it is. There are 3 elements of this that I can add together to get a prime. Namely, for example, there are actually lots of choices, but 2 plus 2 plus 9. And I want to note here one thing that I think is hopefully clear is that if I add more elements to this set, is it going to change whether it's a P3 set or not? Right, it cannot possibly make it not a P3 set, because no matter how many digits I add, if I go ahead and throw in 163, 1729, and a million, this is still a P3 set, because it still has 2 and 9 in it, so it still has 2 plus 2 plus 9 is 13. So being a P3 set is a statement about having a collection of elements with a certain specific property. And so if you add elements, those elements are still in it. So my hope is that that is sufficient to answer or to give you some thought about what a P3 set is. And then 49 is a follow-up. 49 is about the core of a P3 set, and so for a P3 set S, the core of S is defined to be the set of little s in big S, such that S minus little s is not a P3 set. Okay, so let's calculate the core of this S. Not with these things in it, just those. I don't want to decide if 1,000,009 is prime. So let's calculate the core of 2, 5, and 9. And so to do that, I'm going to have to contemplate what it would look like if I removed each element from this set. If I removed S was 2, I would have 5 and 9. If I removed S was 5, I would have 2 and 9. And if I removed S was 9, I would have 2 and 5. Okay. Is 5, 9 a P3 set? Yes, it is, because, say, for example, 5 plus 5 plus 9 is 19. Or if you prefer, 5 plus 9 plus 9 is 23. Either way. Okay. So this is a P3 set. And so what that's saying is S equals 2 is not in the core, right? Because I'm looking for things that I could pull out of the set and leave myself with not having a P3 set. Okay, so this is not in the core. Okay. 2, 9 is a P3 set for, in fact, the same reason I wrote down earlier. Namely because 2 plus 2 plus 9 is 13, and that's prime. Okay. Again, even when I remove 5, this is still a P3 set. So that's not in the core. And is 2, 5 a P3 set? And this is not a P3 set. There's only a handful of possibilities. In fact, I believe these are all the possibilities of things that I could get out of sums of 3 elements of this set. This one is 6, that one's 15, this one's 12, and... oh, sorry, I wrote down the same one twice. This one should have been... this one is 9, and this one is 12. And, well, that doesn't work. All of these happen to be divisible by 3. Okay. So, because this is not a P3 set, this is in the core. And so what we've just calculated is that, in fact, the core of the P3 set 259 is the set whose only element is 9. And so one way to think about what the core is describing is the core is describing the set of elements of your set that appear in every way of writing down a prime. And so in this particular instance, 9 happens to appear in every previous example, because if you look at the original set, it turns out the only way you can sum a prime out of these has to involve using 9 if you're going to throw 3 of them together. So that is what's happening with this question about the core. Okay. Questions about P3 sets and cores? Okay, 48 is to modify Euclid's proof to show that there are infinitely many primes of the form 3k plus 2. Okay, so I gave you a hint about this in the video, but I will go one word further than I went in the video. So suppose for sake of contradiction there are finitely many. Call them P1, P2, up to Pn, say. So the thing I want to consider is the number n. And so the thing I told you in the video is that unlike Euclid's proof, where Euclid added 1 here, you specifically want to subtract 1 here. Sorry, plus 2. Not minus 2. That will help. It happens to make this proof actually work. So I want to consider this. The thing I did not tell you in the video, but I will give you as an additional hint, is you want to put a 3 here. And so what you need to prove in order to finish this, just like Euclid did, is you need to prove that this number has to be divisible by a prime of the form 3k plus 2 that is not in your list. Thomas asks, wait, isn't this 47? And so herein is where it is a problem that I mismatched the parts of one of the questions with what number the question was. So when I fixed that, I slightly changed the order of questions 46, 47, and 48. So this was 47, or sorry, this is now 47, whereas it was before 48. So 48, 47. But I am taking that when people wrote numbers before, they were writing the numbers in the old file and not the numbers in the new file, because the new file wasn't posted yet when people submitted this. So I think the questioner wanted to know about what is in the new version 47. Sorry about this. This was a big disaster in terms of consistency of problem numbering. Eight, 49. Okay, and now we have made it out of these questions. And so we're now talking about question 51. Let's see, there's a specific part of 51. I think 51A, yeah. Okay, so 51 is about balanced sets, where a balanced set is a finite subset of S. Sorry. Subset S of Z plus such that the size of S intersect Z plus is the same as the size of S intersect Z minus. So, for example, this is definitely balanced. Because for this set, the positive intersection gives me 1 and 101. And the negative intersection gives me -7 and -2. So in this instance, both of these have size 2. They're equal, so this set is balanced. Whereas this would not be balanced. And why is it not balanced? It's not balanced because if I calculate this intersection, I would get 2, 4, 19, which is 3 things. Whereas if I calculate this intersection, I would get -7, -3, which is 2 things. Okay, and so the question specifically was, can we do 51A, which is prove that if A is balanced, so is A union 0. Okay, so let's suppose A is balanced. And let's let B equal A union 0. So this B is the set I want to show is balanced. So what is it I need to show? I need to show that the size of B intersect Z plus is the same as the size of B intersect Z minus. Okay, so let's consider the size of B intersect Z plus. This is, in fact, the same as the size of A union 0 intersect Z plus. And so it's worth noting 0 is not in Z plus. So this intersection is, in fact, the same as the intersection A intersect Z plus. Okay. This equals is because 0 is not an element of Z plus. This is the same as the size of A intersect Z minus. This equals is because A is balanced. So now this is the same as the size of A union 0 intersect Z minus. This is because 0 is not in Z minus. And this is, well, now this is by definition, this is the size of B intersect Z minus. And so what have we shown? We've shown the size of B intersect Z plus is the same as the size of B intersect Z minus. And so therefore we've shown that B is balanced, which is what we wanted. Okay, I think I've answered every question that was submitted on Katie, but I'm willing to guess there are probably more questions. So I am happy to entertain if there are more questions to talk about any of the remaining things. But if there are no more questions, then I'm happy to leave it here, but I'll wait a while and see if anyone has any other questions. Should we write up these notes about why the sets are equal when typing up the proof? Yes, absolutely, but you don't have to type them in line. So you could say, write down the string of equalities, and then at the end write where the first equality follows because 0 is not an element of Z plus, the second equality follows because A is balanced, and so on like that is probably the way to type it that is not arduous for you, and I am all in favor of making things not arduous for you. to the extent possible. Okay, so someone asked about 45. So I originally put 45 on here in the hopes that it would be a proof by a proof by contradiction, but it turns out you do not need to do contradiction. You can do proof by contrapositive. So the contrapositive here is if x and y are real numbers and 2 root xy is greater than x plus y, then x is less than or equal to 0, or y is less than or equal to 0. And so what do? You look at this inequality, you square both sides, and then you look at what happens with your algebra. (48G). 48G asks you to prove or disprove every infinite subset of the positive integers is a P3 set. And so someone asks, how would you start this? And so here's my hint. It's false. Try to come up with an infinite set that you can very easily prove cannot possibly be a P3 set. You might, for example, look at question F immediately above it. There you go. (35B). Yes. Let's see, so here 35B is going back to this question about non-differential. And so a subset of the positive integers, or just of the integers? Yeah, so S a subset of Z, called non-differential, for all x and y in S, have x minus y is not in S. And so then 35B says and I'll go ahead and just short circuit it's true, prove that if, is it S and T? Oh, I guess it doesn't give the names. Prove if A and B are non-differential sets, then so is A intersect B. Okay, so to do this, I'm going to suppose A is non-differential and B is a set. It will transpire in a moment that B doesn't need to be non-differential, that is an unnecessary hypothesis, so that is why I'm writing it this way. But if you were doing this for the first time, you would probably not know that. And let's let C equal A intersect B. The thing I want to show is that C is non-differential. So that is, I want to show that if X and Y are in C, then X minus Y is not in C. So that tells me what I need to do, which is to suppose X and Y are in C. So X and Y are in A, because C is A intersect B. And so X minus Y is not in A, because A is non-differential. And so, because A is non-differential, X minus Y is not in A, and so X minus Y is therefore not in C, because C is the intersection of A and B. And that completes the proof, because I've now shown that if X and Y are in C, then X minus Y is not in C. And so what's really happening here, if you want to dig deep into what's happening logically, is that because being non-differential is a statement about every element or every pair of elements in the set, every subset of a non-differential set is in fact automatically non-differential, because all of the pairs of elements in a subset are also in the superset. And so, in particular, the intersection of two sets is a subset of both. And so if I take the intersection of two sets, if either set is non-differential, automatically the intersection is. Okay, let's write down a proof of 34. Okay, so A and B here are subsets of R, which we've decided is our universal set for this problem. Okay, and we want to prove that A union B complement is all of R if and only if B is a subset of A. Okay, so this if and only if means I have to prove two directions, so I'll do this one first. So that is, I'm proving that if A union B complement is equal to R, then B is a subset of A. So that is to say, I'm going to suppose that A union B complement is R. And the thing I want to show is that B is a subset of A, which is to say that if X is in B, then X is in A. Okay, and all I'm doing here is just writing out the logic of what it is I need to show. Again, probably in the typed version, I would not write this part. Okay. So in particular, I need to suppose that X is in B. Okay. So because X is in B, it's not in B complement. But by assumption, X is in A union B complement. Okay, because X is in R. That is the reason why that I've assumed this. And so thus, since X is in the union, but it's not in that one, it must be in this one. Okay. And that's what I was trying to get from. I was trying to get from X is in B to X is in A. Huzzah. Okay, so that's that direction, which I think specifically was not the direction that was actually asked about, but I just figured I'd go over the whole question. So other direction is we want to show that if B is a subset of A, then A union B complement is all of the reals. Okay, so we'll suppose B is a subset of A. And now I want to show that these two sets are equal. Sorry, I actually wrote that there. I don't need to put that there. I want to show that these two sets are equal, so I need to do that by mutual inclusion. So I need to show you that inclusion and the other inclusion. Okay. So let's write down this inclusion first. Okay. So I'm going to suppose that X is in A union B complement. And we want to show that X is in fact an element of R. Well, A is a subset of R. And B complement is just a fancy way to write R minus B. So that's certainly a subset of R. And so X is in R, regardless of whether regardless of whether X is in A or X is in B complement. Sorry, I wrote this in a way that's kind of ugly. Let me, I'll stand by that. But let me write this in a way that's a little more clean. Since X is in A union B complement, X is in A, or X is in B complement. Okay. But then by the above, if X is in A, then X is in R, because A is a subset of R. If X is in B complement, then X is in R, because B complement is a subset of R. Okay, this is not the most beautiful write-up anyone has ever done, but I think this will do. Note, by the way, what I've really done here is cases, but I haven't broken it out into cases because the argument for each case is half a line. So you do not always, just because you're breaking apart an OR, necessarily need to write it out as cases. If it's short enough, you will sometimes do it in line. Of course, there's nothing wrong with doing it just written out in cases if you want. Okay, and so now I need to show the other direction, which is I need to show that if X is in R, then, in fact, X is in A union B complement. Now, it's important here to remember, I have this hypothesis up here. And if you look at this piece, I did not use that hypothesis at all. In fact, this direction, the fact that A union B complement is a subset of R, in fact, has nothing to do with anything I assumed about the relationship between A and B. That entirely comes from the fact that I assumed that A is a subset of B and B is R minus B. Sorry, B complement is R minus B. So both of these things are subsets of R. So it really doesn't have anything to do with that. This one, though, this one becomes interesting. Okay. So really, there's two possibilities here. My case one is that X is in A. Okay. If X is in A, then definitely X is in A union B complement. And then I'm done. My second case is that X is not in A. And this is the case wherein I have to use the relationship between B and A. Okay, so here's where I have to say, since we assumed B is a subset of A, that, in fact, what does this tell us? X is not in B either. Okay, why is this? If you want to really spell this out, B is a subset of A means if X is in B, then X is in A. And so the contrapositive of that is if X is not in A, then X is not in B. Okay, so that's the logic, if you're curious about the logic of why telling me that X is not in A tells me it's not in B. But X is in R and not B. Thus, X is in B complement. And so X is in A union B complement. And so then we're done. Okay, so that is 34. I mean, you explicitly told me to choose cases for A in the question, so that's why I chose cases for A. But I would definitely choose cases for A because the thing I'm trying to prove is that X is in A union B complement. And so the one piece is I'm automatically done as soon as X is in A. And so this is often how you end up coming up with cases, is you see, okay, well, if X is in A, then I'm done right away. And so then I just have to consider what happens if X isn't in A. And so that's sometimes how you sort of fall into cases. Okay. So 31. 31 asks us to show that every integer can be written as a sum of 3 distinct integers. Okay, so the key here, at least to one way of doing this question, there are many correct solutions to this question, but the key to what I think is the most straightforward solution is to note that if n is a multiple of 3, I know how to do this. Okay, so basically here I'm using the division algorithm to say that there exists a k such that n is 3k, or n is 3k plus 1, or n is 3k plus 2. So in the 3k case, that is the 0 mod 3 bucket, if you want to give it a name, then we can take x to be k minus 1, y to be k, z to be k plus 1, and then the sum of these is n. This, by the way, this is something you stumbled upon in the proof of number 33. It was not intentional, by the way, in this particular instance, that the hint to number 31 was in number 33, although in general, you do want to look through sort of the entire homework assignment because things may not happen in order because, well, in life, facts don't come at you in a particular order. Facts just come at you. But in this particular instance, I specifically intended that you do 33 before 31. And then when I was moving problems around, I moved them around in such a way that that didn't happen. So apologies about that. But that handles the first case. And so what do I do if n is 3k plus 1? Well, then I modify this slightly. Namely, instead of taking z to be k plus 1, I'm going to take z to be k plus 2. And so the point here is I'm choosing these three numbers because these numbers are definitely different, right? This number is 1 more than x. This number is 3 more than x. So they cannot possibly end up accidentally being equal. And then for case 3, what can we do? Well, we could say n is 3k plus 2, so you can take x to be k minus 1, y to be k, and z to be k plus 3. And again, these three are distinct, and they add together to be n. Okay. Again, the art here is figuring out how to break this into cases. And that's actually really the point of this question, is that no part of this question really gives you a hint that you're supposed to be looking at the mod 3 buckets. But if you play with it and think about other things you know and let it soak in for a bit, you maybe sort of stumble into the fact that you can do one of these cases. And then that sort of organically lets you feel out what the other cases can be and how you can handle those. But unfortunately, as much as I would like it to be the case, in real life when you're doing something and you're supposed to break into cases, there is not a giant flashing sign that says so. And so sometimes you just have to try it or figure it out or whatever. And so that's part of the point of this question, is to give you sort of a sense of what it's like to feel out what kinds of cases might help you. As it happens, I have, by the way, seen someone write down a proof of this with like 6 cases, and I have seen someone write down a proof of this with no cases. So this is certainly not the only solution. It is just the one that is sort of most suggested by question 33. Any other questions we wish to revisit? $45. Okay, so let's write down some scratch work for 45. So let's write down that. If I square both sides, I get x squared plus 2xy plus y squared is less than 4xy. And so then I will get x squared minus 2xy plus y squared is less than 0. So then that will be x minus y squared is less than 0. And there is your problem. So I think this is sort of a nice proof by contradiction outline if you want, but you can also write this up as a proof by contrapositive if you want. That is up to you. But this is basically the point is that when you square both sides of this, you end up in this zone where you end up with a square that's being less than 0, and you can't square a real number and get something less than 0. It's very easy to do because there are no flags that sort of tell you how hard the thing you're looking at is supposed to be, and so it is very easy to way overthink something, or vice versa. Uh, this is just a thing that happens in life, unfortunately. Any other questions that people are stuck on or want to talk about? Alrighty, well, let's wrap up there for the day. Have a wonderful time wherever you go or don't go. Have a wonderful holiday break, I guess I should say. Uh, Remember, we just got an email today that says we'll be online again starting on the 3rd of January, but then hopefully we'll come back to campus on the 11th of January. We'll see exactly how these things go, but that's the plan as things currently sit. Uh, at such a point as we are back on campus, I intend to keep the structure of the course relatively the same, where I'll post the lecture videos to YouTube so that if you're in quarantine or whatever and you can't come, then you can still watch those and still have them as a reference to look back to, because people tell me that's useful. But then I'll do this thing that I'm doing right now where I talk about questions in the homework, do extra examples and all that kind of thing. I'll do that in person if we're on campus and let you ask questions and all of that good, juicy stuff. So that's basically how I plan to keep the structure of this class. So it should be relatively similar, all things considered, but we'll actually get to see each other, which is lovely sounding at this point. Anyway, have a wonderful break. We'll deal with what happens when we get back after that. Email me if you have any more questions. But if not, I will see you in January after the new year, when 2020 is finally over.